Hey, welcome back everybody. Today we are going to begin working on chapter 6, which is all about kinetics and equilibrium. Kinetics is the study of what makes a chemical reaction happen, like what has to happen in order for the reaction to go, because you can mix some things together and they react, and other things you mix together and they don't react. And even the things that do react when you mix them together, what specifically, like on the atomic level, has to happen for a chemical reaction to happen? And also, how can we speed things up, or how can we slow things down, right? Because the process of getting energy out of sugar is sort of the same process of lighting something on fire, and maybe we don't want that to happen inside our body, so there's ways we can speed things up, there's ways we can slow things down. We want to know why this happened, how does this even happen? And then there's this idea of equilibrium. And I know everybody learned about this crazy word in biology called homeostasis. Lord, how many times was that word hammered into your head? Well, homeostasis is based, you know what that is, when everything kind of equals out and is balanced. Well, the same thing happens on the chemical level, way down on the atomic level. And it's when these chemical reactions reach the state of what we call the equilibrium, where they have kind of balanced out, that we get homeostasis in these big giant organisms and whatnot. So equilibrium is when a chemical reaction goes forward, but it can also be reversed. Like oxygen in our blood. Oxygen can dissolve into our blood, and then oxygen comes out of our blood, which is very good, because oxygen goes into our blood, in our lungs, and then out of our blood, in our body and stuff. So once that hits a nice equilibrium, that's when we're happy. And that's what we're looking at, how things get equal or balanced out when they can go both forward and reverse. But in this case, we're not going to look at the macro level of a living organism. We're going to zoom in way down to what happens at each individual chemical reaction level. You guys with me? Sweet! That's awesome. So let's get going. Let's learn some stuff with chapter 6, all about kinetics and equilibrium. And the first word that we're going to learn is this one: kinetics. So kinetics is the study of the rates of chemical reactions. So rates, this thing right here. So this is the speed of a chemical reaction. What can we do to speed things up? What can we do to slow things down? And also how they happen. How do chemical reactions actually happen? This is what we're going to be looking at. Sorry, minor glitch. But anyway, so what we get, so actually what we need to talk about first is this thing called collision theory. So collision theory states that in order for a reaction to occur, the particles have to collide. In other words, they need to bump into each other with enough energy and the proper spatial orientation. So we need two things here. We need enough energy, and we need this thing, spatial orientation, in order for a reaction to occur. Now I got a big old picture of a key right now. What's a picture of a key doing right there? Well, this kind of captures the idea. You can take a key, you can throw it at a lock, and it's not going to do anything really, right? So that means so for a key to work, it has to line up perfectly, right? So the key has to line up with the keyhole, right? So that's spatial orientation. It has to line up just right. It can hit sideways. Nope. It can hit backwards. Nope. It has to line up just right in order for the key to go into the slot. Get it? And also, you can't just daintily sort of hold the key there. You got to push the key in. So there has to be enough force to get the key to go into the lock, and it has to be lined up just right. It is remarkably similar with a chemical reaction. And so when that happens, when things are lined up just right and they hit with enough force, we get this thing, an effective collision. Now this term is very elusive, an effective collision. It is basically a collision that's pretty effective. It's a collision that results in a chemical reaction. So here we have a pretty good example of what an effective collision looks like. So up top, here we have carbon monoxide, and here is nitrogen dioxide. Now, when carbon monoxide and nitrogen dioxide collide, they can form carbon dioxide and nitrogen monoxide. They do so because these products are far more stable. But if you see here, you see the carbon has to line up with one of the oxygens in order for this carbon to grab a hold of that oxygen. Does that make sense? And what happens is that, like right in here, there's a big thing where they collide, and when they collide, the reason why they need to have enough force is because when they smash together, they have to smash together so hard that they break all the chemical bonds. Well, at least not all of them, but at least like when they hit, they need to hit so hard that like this oxygen and this nitrogen break. So they have to hit hard enough to break chemical bonds. That's what we mean by they have to collide with enough force, and the proper spatial orientation means that like the things that are going to stick together have to be lined up right. And so here's this big collision, right? They smash together and they break apart, and they make this little explosion of molecules, but as they're exploding out, you know, they're atoms and molecules, so they're made out of protons and electrons. And so all the protons are pulling on all the electrons, and all the electrons are pulling on the protons, and so it kind of explodes out and then snaps right back together because there's that attractive force of the protons and electrons. It's kind of trippy to think about. But if they collide hard enough to break the bonds that are already there, like to break the old bonds, right? If they do that, they blow up. And if they're lined up just right, when they snap back together, they snap back together into these new products. Does that make sense? That is an effective collision. So yes. But now if you look at this one down here, at this situation, they could be coming together and smashing just as hard, right? Bam, they explode. But when they snap back together, they weren't lined up right. They weren't lined up in such a way that the carbon could grab an oxygen. Here it's like the carbon smacking into the nitrogen, and nope, they're not going to bond, just for various reasons that don't really matter to us. But that is not an effective collision. That's a collision, but it's not what we call an effective collision. It's not going to react or result in a chemical change because we need two things: enough energy and proper spatial orientation. Now, energy tells us how hard they're smashing together. They got to smash together hard enough to break the chemical bonds that are already there, and they got to be lined up just right so when they snap back together after this like explosion of broken chemical bonds and whatnot, they got to snap back together in a way to make a new product. Got it? Great. So an effective collision basically is a collision that results in a chemical reaction. That's not too highfalutin. So this is also not rocket science, but if you want to make the chemical reaction go faster, you have to have more effective collisions, right? So the greater the rate, or, you know, like, remember we said this is the speed. The greater the rate of effective collisions, the greater the reaction rate, right? So the more of these reactions you can create, the faster the chemical reaction is going to go. And if you want to make more effective collisions, let's come back up here to look at this for a minute. In fact, a collision that results in a reaction. But collision theory says that in order for that to happen, we're going to need spatial orientation and energy. So those are the two things that we need. So there are only two ways, things that we can tweak to make a chemical reaction go faster. We have to have more energy, right? And so more energy is like temperature, right? They got to smash together fast enough to break apart. And so the only thing we can do here is make things warmer. But that makes spatial orientation. Can we line things up right? We're going to talk about later on how we can do that, because we can tweak these things to make things go faster. I mean, obviously. And we will find out what and how to make that happen. How we can make more effective collisions happen. And so this gives us this idea, right? So wait, before you go in there, we kind of like up here, you see, I just was like, oh, there's this, oh, it's an explosion, right? So we just go reactants, products, bing, bang, boom, right? But it's not like that. It's like the reactants don't just magically turn into products. There is something in between. And that is where we have this thing called transition state theory. It means that there are intermediate products, and for us, in a chemical reaction, it is called the activated complex. Intermediate products form during chemical reactions. and they exist only, when I say briefly, I mean like a billionth of a second. They're like hardly even there. All right, and this is, like, this, again, I mean, this might sound weird to you because we're talking about atoms and chemical reactions, but guys, we see this all the time. Like, this is like, atoms are matter just like everything else. And so when we go to bake chocolate chip cookies, this is sort of like transition state theory when we bake chocolate chip cookies. Because look, when we bake chocolate chip cookies, right, we have, whoa, jeebers, we have ingredients, right? So we have ingredients, we have step 1, and then we have cookies, step 2, right? Well, no, that's really not what happens. We have to have this. We have to have the cookie dough, right? The ingredients don't just magically snap into cookies. That would be lovely. That would be like pure magic. And I wish that that life was like Harry Potter, but it's not. We can't just blink, snap, and then there will be cookies. We have to like make this stuff. And so the cookie dough, is kind of like the activated complex for chemical reactions. It's the thing that exists in between, right? And then, so these are the reactants, and here is the products, and this thing right here, that's like our activated complex. There's something in between the reactants and products. It doesn't just blink. There's something in between, and that something in between is what we call the activated complex. It exists for a billionth of a second. I think you guys get the idea, but in a chemical reaction, the activated complex is going to be defined a little bit differently. It is what we call a high energy transition product. It is kind of like that explosion that exists when our two reactants smash together and break their chemical bonds and explode out and start to implode in. That's what we call the activated complex. It's that middle part where all the chemical bonds are broken, the reactants are like blasted to bits, and they're just about to snap back to make our new products. That's what we call the activated complex. It is the thing that exists in between reactants and products. That's what the activated complex is. You guys dig what I'm saying? Now, there are a couple of things that we have to have dialed in for the activated complex. The first thing is we do need to know that it is high energy. Like, it contains a boat ton of energy because it's made from, the reactants are flying around, they have tons and tons of kinetic energy, and then boom, all that kinetic energy is converted into potential energy as they sort of break apart and explode into this ball of like part reactant, part product explosion. All that kinetic energy, all that heat energy is potential energy. It gets kind of converted briefly. And we need to know that it is a transition product. In other words, it exists in the middle, right? It's not going to be around for very long. It's what gets us from point A to point B. It's what gets us from reactant to product. And here are some things that we need to know about the activated complex. First, it is very, very high energy. Okay, all of the kinetic energy has been converted to potential energy, and it's like, and it's formed from this high energy collision. So the collision has to have a lot of energy. The second thing we need to know is it is very unstable, which means it will be temporary. Like a billionth of a second, a millionth of a second. The actual length doesn't matter. It's pretty gosh darn quick is what we need to know. It's like a flash in the pan. So as soon as it sort of forms, it falls apart. So the reactants come in, and as soon as they collide, they like that activated complex is created, and as soon as it's created, it starts to fall apart. And usually, and I'm going to want you to see this usually, I did not say always. See, I did not say always for a reason. And I want you to like lock that in. That usually it rearranges to form products. Usually. However, the activated complex can go back. It can go back to make the reactants. And when that happens, you have no effective collision. Got it? That's great. So again, activated complex, it's that intermediate high energy thing that's in between reactants and products. It is very, very high energy, and it's formed because it's formed from high energy collision. All the kinetic energy gets turned into potential energy. It is very, very unstable because it's all that potential energy, and it's literally like an explosion. So it like falls apart immediately, and for the most part, usually it comes together, it coalesces together into new products. But not always, because sometimes the reactants collide to make the activated complex, and it goes right back to products. And we have evidence to support this. This isn't stuff that we're just like, oh, maybe, because that doesn't work. Science, evidence. And there is, and we will talk about some of that later. And so here's a new word for us, activation energy. So activation energy is a word that I think most of us are pretty gosh darn familiar with. Like, we know what it is. It's the energy needed to form the activated complex. This is the definition. I want you to remember that. But it's like it's also the energy needed to start the chemical reaction. So like paper or like a candle, like they don't just ignite on their own. They need a little bit of activation energy. And so when we take a match to a candle wick, we are providing activation energy. In other words, we're providing enough energy to make that first activated complex so it snaps back together, and then that chain reaction of combustion can start. But we need a little bit of energy to get that first activated complex going, and it is called the activation energy. This is also referred to as the energy barrier reactants must overcome to form products. It's the energy they need to absorb to become that high energy, like, activated complex. Does that make sense, y'all? I'm certain it does. So the next thing we need to learn no, wait, that's it? That's all we got? I think we better review really quick here, because that was a lot of stuff to smash into our brain. Not really. We need to know kinetics, right? It's the study of the rates of chemical reactions and how they happen, which is the first half of our chapter. Equilibrium is going to be part 2. And so the first thing we got to know is collision theory, because this is how a chemical reaction happens. Chemical reactions happen by the products smashing together with enough energy, and it's going to be kinetic energy, like heat, to break apart and form this activated complex, right? So not just energy, but also spatial orientation. So they need to be lined up. It's sort of like when train cars hit together and they link. Those linkages have to be lined up just right. If they come in like this, they're not going to work. If they come in like this, it's not good. They have to be lined up just right, in order to work, and they have to have enough energy to be able to form that activated complex. So 2 things, energy and proper spatial orientation. Energy to break bonds, and proper spatial orientation so that everything's lined up to make the products that we want. And when that happens, we have a thing called an effective collision, which is a collision that results in a chemical reaction. And we can see right here, wait, hold on. There. Now you can see how things need to be like lined up, right? So for these 2 things to actually happen, we need to have them like lined up so they can form a bond when that activation complex sort of like collapses into the products. And so to make something faster, to make a chemical reaction faster, you just make the effective collisions happen more often. So the more often you have an effective collision, the more often you have a chemical reaction. And we can't forget about the activated complex, or transition state theory. And again, theory in the science world is not a guess. This is an explanation based on natural law, so laws of nature. And this is how we explain how they interact. And what that means is, between reactants and products, there is something in between. It's not like a magical pop from one thing to the other. And that in-between thing for chemical reactions we call the activated complex, which is a high-energy transition product. It is super high energy because all the kinetic energy is turned to potential energy. It is very unstable because it's so high energy, and as soon as it's made, it like falls apart. And as the activated complex falls apart, it usually forms products, but sometimes goes back and makes reactants again. And the last thing we looked at was activation energy, which is defined as the energy needed to make the activated complex, right? So, and that kind of gets things going. That's the amount of energy it takes to get a chemical reaction started. And then, that's it. So, what I want us to work on, to get these ideas mulling through our brain and think about them, are these things. And this is going to sort of relate our everyday lives to these chemical reactions, because these concepts we see in our everyday world, they also apply to the very, very small world of chemical reactions. and also transition state theory. That's where we're going to dig into like the activated complex and like what it does, how it do, and what it means, and all that kind of good stuff. And I will see you next time we're working on those. Thanks for tuning in. I hope you guys have a super awesome day. I already am. And I'm sure you will too.